In the study of geometry, we bring order to completely empty space with a single precise cut, a line. We know that if we measure a specific line, we can calculate its exact mathematical slope. But does the logic hold in reverse? If you are given only a calculated slope, can you pinpoint that exact line in space? Here is a Cartesian plane. We plot a single line, use its coordinates, and determine its slope, m, is exactly -1. But the value of -1 does not belong exclusively to our initial line. There are an infinite number of lines that slide freely along the y-axis, entirely filling the grid, that generate that exact same slope. Look at how they sit on the plane. Every single one of these vertically stacked lines shares the exact same angle of inclination relative to the x-axis. Let's label that angle alpha. Because inclination is strictly constrained between 0 and 180 degrees, the tangent of that angle has only one possible value. Slope is just the tangent of the inclination. Therefore, matching physical inclinations guarantee matching slopes. A slope value cannot tell you where a line is, it only dictates its orientation. But while a single slope leaves a line's position completely ambiguous, comparing the orientations of two slopes provides the mathematical machinery required to map exactly how any lines in a 2D plane interact. To see how that machinery works, we can build a test environment. Two independent, non-vertical lines, an orange L1 and a blue L2. First, we measure their physical angles to the horizontal axis. L1 has an inclination of alpha. L2 has an inclination of beta. Visually, if we want these two paths to run entirely parallel without intersecting, their physical angles to the axis must be identical. We translate that visual reality directly into algebra. If angle alpha equals angle beta, then the tangent of alpha must equal the tangent of beta. The tangent of alpha is simply the slope of line 1, m1. The tangent of beta is m2. The only place this logic fails is with perfectly vertical lines. At exactly 90 degrees, the tangent function is mathematically undefined, rendering the concept of slope useless. But outside of vertical anomalies, the algebraic equality of slopes, m1 equals m2, is the irrefutable guarantee of a parallel geometric trajectory. We can shift this experiment from parallel separation to direct intersection. We anchor L2 on top of L1 and rotate it until it locks into a perfect 90-degree perpendicular cross. By rotating the line, we increase its angle to the x-axis. The new inclination, beta, is now exactly alpha plus 90 degrees. Now, we need to find the exact algebraic relationship between these two intersecting lines using their tangent functions. The tangent of beta equals the tangent of 90 degrees plus alpha. Adding 90 degrees to a tangent function alters its output entirely. By trigonometric identity, the tangent of 90 plus alpha becomes the negative cotangent of alpha, and negative cotangent can be rewritten as -1 divided by the tangent of alpha. Now we substitute our original variables back in. The tangent of beta is our second slope, m2. The tangent of alpha is our first slope, m1. We get m2 equals -1 divided by m1. We multiply both sides by m1 to lock in a clean algebraic condition. If the product of two slopes equals -1, a perfect 90-degree intersection is guaranteed. The geometry of the cross is determined by this specific numerical product. Parallel and perpendicular lines represent the limit cases of geometric interaction, the 0-degree and 90-degree extremes. What happens when L2 breaks free and settles at an arbitrary non-vertical angle of intersection? The intersecting lines and the x-axis now form a triangle. We identify theta, the acute interior angle where the two lines meet. By applying the exterior angle theorem, we prove that theta is simply the difference between their individual inclinations, alpha 2 minus alpha 1. We initiate the algebraic translation by taking the tangent of this geometric difference. The tangent of alpha 2 minus alpha 1 expands into a standard identity, the difference of the tangents divided by 1 plus their product. When we map our slope variables onto these tangent terms, we reveal the master formula for intersections. Look at the constraint in the denominator, 1 plus m1 times m2. If the lines were perfectly perpendicular, that product would be -1. The denominator would become 0, making the tangent undefined, which perfectly aligns with the 90-degree rule we established earlier. And because any intersection creates an adjacent supplementary angle, calculating it simply negates the numerator, swapping it to m1 minus m2. By including two slope variables into this master equation, we mathematically calculate the exact angular reality of any line intersection in a 2D plane. We shift this logic from continuous lines to discrete coordinates, point A, B, and C. Connecting the first two creates a line segment with a specific slope, MAB. Connecting the next two creates a separate segment with its own calculation, MBC. What if the algebraic calculation determines that the slope of AB is mathematically identical to the slope of BC? We established early on that equal slopes strictly mandate parallel geometries. Segment BC must correct its trajectory until it is perfectly parallel in orientation to segment AB. But there's a physical constraint. They share a common vertex at point B. Locked at that anchor, the parallel segments physically snap together, merging into a single continuous line extending through A, B, and C. This phenomenon is known strictly as collinearity. While a single slope cannot fix a position on a grid, the relationship between slopes determines the structure of the plane. It calculates exactly how those lines intersect and proves definitively whether isolated points belong to the same path.